In this video, I'd like to introduce nucleophilic substitution. And this is a profoundly important reaction mechanism, and it's really fundamental to almost every reaction you encounter in organic chemistry. And so it's really important that you learn and master this type of reaction. And I think the way to begin here is to simply introduce a couple of terms and a very simple reaction arrow. So here we have a nucleophile and an electrophile. We draw this arrow here. The arrow means that the lone pair on the nucleophile is attacking the electrophile and forming a bond between the two. So what we draw, of course, is a bond connecting what we're representing as the nucleophile and the electrophile. And as I mentioned in my primer on electrophilic aromatic substitution, one of the things that you're going to encounter in organic chemistry on the regular is this suffix phile. And it comes from the Latin word phyla, or the Greek word philos, which means loving or to love. And translated into this context, what it really adds up to is attracted to. So nucleophile basically just means attracted to nucleus. Electrophile just means attracted to electrons. So the electrophile is attracted to electrons, and the nucleophile is attracted to nuclei. What does it mean to be attracted to nuclei? Well, as you may recall, the nucleus is the site of the electropositive proton, and the electronegative electrons sort of surround the nucleus, contributing to a balance of charge in the atom. But the nucleus is the site of the positive charge. So nucleophile really just means attracted to a positive charge. So nucleophile is attracted to positive charge. Electrophile is attracted to electrons. So the electrophile is always going to be electropositive, and the nucleophile will have an abundance of negative charge. That's generally how it goes. So this is the general scheme of not just nucleophilic substitution, but a general attack in chemistry. And this attack will break down in three typical ways. And the first is this. We have a bonding pair of electrons and a pi bond in an aromatic system, do the attack we just drew. And this is electrophilic aromatic substitution. And I have a series of videos on this subject. This is not what we're going to be encountering in this set of videos on nucleophilic substitution. The second instance where we can have an attack like this is when we have an isolated double bond attacking an electrophile like this. And of course, this is known, but this is generally the province of addition reactions. And I will do a series of videos on addition reactions as well. And we're not going to really be focusing on addition reactions here. The third is when the nucleophile is a lone pair, which is what we're covering here. And this is generally the province of nucleophilic substitution. And this is what we're going to be focusing on in this series of videos on the subject. So this here. And so to sum up, a nucleophile attacking an electrophile, as I've shown here, is basically just a source of electrons attacking something that's electropositive. And that source of electrons can come from a pi bond. They can come from bonding electrons in an aromatic system. It can come from pi bonding electrons in an isolated double bond, or it can come from a lone pair. And what we're focusing on here is the lone pair. Okay, so for this subject, there's two key reaction mechanisms. There's SN1, and there is SN2. And I'll make individual videos on both of these reaction mechanisms, but I'd like to just outline what the S and N stand for. So this stands for nucleophilic substitution unimolecular. This one stands for the same but bimolecular. molecular. And what it refers to is the rate determining step in an SN1 reaction is unimolecular, and the rate determining step in an SN2 reaction is bimolecular. And I won't really delve into any details in this primer video, but when we look at SN1 and SN2 in their own videos, I'll go through this in detail. And basically, let's go through both of these reactions at a very high level. So in an SN1 reaction, what you have is a leaving group, and the leaving group is going to leave. And of course, what you generate is a carbocation and the leaving group. And the nucleophile, which in a case like this is typically going to be a solvent, comes in and it traps the carbocation. And what you get is you get your substitution. So we've substituted this leaving group for a nucleophile. And as I mentioned, when we get to SN1 videos, I'll go over this in considerably more detail. SN2 is a little bit different. So for SN2, we have our leaving group and we have a nucleophile. And the nucleophile comes in and attacks from the backside and displaces the leaving group. And here you can see why the rate determining step is bimolecular in the case of SN2, because we have a nucleophile and a leaving group involved in the rate determining step. With the SN1 reaction, this is the rate determining step here, the leaving group leaving. And there's just only one molecule involved in that process. So that rate determining step is unimolecular. That's what it means. In any case, the product here is just this plus our leaving group. So that's SN1 and SN2 at a very sort of high level. And this is, as I mentioned before, we are looking at the process of a source of electrons attacking an electrophile, but we're focusing our attention on this right here. And what we're going to find is that the source of electrons is typically coming from a lone pair in this case. And when it comes to the source of electrons being a pi bond, these are different reaction mechanisms. They're electrophilic aromatic substitution or addition. And as I mentioned, I'll make video series on both of those. Before we go on, though, and end this sort of first primer video, I'd just like to give a concrete example. And let's pick an SN2 reaction. So here is going to be our electrophile. Why is this electrophilic? Well, it's because the bond between C1 and iodine is polarized toward the iodine atom because the iodine is more electronegative. And so what that means is that the C1 carbon is electron deficient. The electron density in the bond is polarized toward the iodine atom, leaving a partial positive at C1. And if we imagine a nucleophile like this, with a very electron-rich sulfur anion, it simply comes in, attacks, displaces the leaving group, and what we get is this. And the reason I want to give a concrete example is because, as you can see, this is how we build up molecular complexity. We have started with two smaller molecules, 1 and 2, and we've generated a larger molecule, 3. And so by using nucleophilic substitution, we're able to very rapidly build up molecular complexity and generate big molecules from small molecules. So this is basically where this fits into the big picture. One last thing to mention is that among the nucleophiles that we're going to encounter, you can imagine this. You can imagine this. You can imagine this. You can imagine this. You can imagine water, of course. You can imagine even something like azide. And in all of these instances, you have a lone pair of electrons, which is going to act as the nucleophile. And what you can see here is some of these are negatively charged and some of them are not. but they all have a lone pair that's going to act as our source of electrons. And our electrophiles are typically going to be alkyl halogens. You can have a primary, you can have a secondary, or you can have a tertiary. And these are typically going to be the electrophiles that we're going to look at for the purposes of this video series on nucleophilic substitution. So that's a very simple primer. And as I mentioned, we will definitely get into more detail on the subject as we move forward and look at all of the individual topics related to this broader umbrella.